Hi, welcome to video 1.3c, even more limits algebraically. So we're at page 68, numbers 59 through 64. It's again just find the limit. And this is going to be a new strategy that we're going to use. So far, when we've gotten 0 over 0, okay, by substitution, when we substitute, so far our two options have been factor and cancel, rationalize, either numerator or denominator. But this is going to be a new strategy, and that is to simplify the expression. So here's an example. Number 60, where you have this expression right here. So remember, the first thing we always do is substitution, and that is a 0 right here. Approaches 0. So we replace x by 0, that'll give us a quarter here. Minus a quarter will give 0. Replace the x in the denominator by 0. So we get the famous 0 over 0. So you certainly can't rationalize, because there's nothing irrational to rationalize. And you're not going to be able to factor. But the one thing you can do is simplify. This is called a complex fraction. It's a fraction within fraction. So I'm going to simplify the numerator. I'm going to find a common denominator of x plus 4 times 4. Then I'm going to say x plus 4 times 4 will give that denominator, multiply the numerator by 4, etc. I'll need to multiply this denominator 4 by x plus 4. So I multiply the top by x plus 4. Be very careful when there's a minus here. That negative will affect both those terms. On the bottom, of course, we just have x. So what happens on the top is we have 4 minus x minus 4. Well, the 4's cancel. So that leaves us with negative x, okay, over 4 times x plus 4 over x. Well, x is x over 1. We're dividing two fractions, so we multiply by the reciprocal of the bottom fraction. And very nicely, the x's cancel. And of course, with the x's gone, we will no longer get 0 over 0. And what happens now is we cancel out the x's, and now we replace the x by 0. We have negative 1 over 4 times 0 plus 4, which is negative 1 over 16. Again, I want to take a second to talk about notation. This expression, the limit as x approaches 0, has to occur at every step as long as there are still x's in the expression. As soon as you get to the point where there are no x's in the expression, that means you do not write the limit as x approaches 0. Number 62, you have limit as delta x goes to 0. Think of delta x not as the product of the symbol delta and the variable x, but as a single quantity, delta x. So you have the limit as delta x as approaches 0 of the parentheses x plus delta x close parentheses squared minus x squared over delta x. So if I do replace delta x by 0, I'll get x squared, because that'll be 0, minus x squared, which gives 0, over delta x gets replaced by 0. So I do end up with 0 over 0. Now I can factor that expression because it is the difference of two squares. So as you know, a squared minus b squared factors into a plus b times a minus b. Now I'm going to show you the factoring method first, and then there is a simplified method as well. So if we start with the factoring method, when I factor a squared minus b squared, it factors into a plus b times a minus b. So that's the square of x plus delta x, and that's the square of x. So I have x plus delta x plus x times x plus delta x minus x, and of course all over my original denominator of delta x. What happens in this second parentheses is the x's cancel, leaving you with delta x times this parentheses over delta x. Well, the beauty of that, of course, is that the delta x's cancel. Now when I replace delta x by 0, remember it's not x that gets replaced by 0, I will get 2x plus 0, and I will get an answer, a final answer of 2x. Same problem. Sorry, this is a bit blurry. I don't quite know. Let's see if I can make it less blurry by making it smaller. I don't know if that's really helping, is it? Anyways, so rather than factoring it, let's actually simplify it. In other words, let's expand this. This is a plus b all squared. That's going to give a squared plus 2ab plus b squared. And then, of course, you have the minus x squared. The x squares will cancel. You'll notice that you'll still get 0 plus 0 squared over 0. But now I can factor out the delta x. When I factor out the delta x on the top, I'll have 2x plus delta x. These delta x's now cancel. Now replace the delta x by 0 by substitution, and 2x plus 0 is 2x. We get the same answer as we got the last time. Now, this is going to get into some weirdness. We're still in 1.3, not for much longer. The limit as x approaches pi of sine x over x. Again, first attempt substitution gives us sine pi over pi. This one's actually very straightforward. The sine of pi, of course, is 0 over pi, and 0 over pi is 0. However, what happens if you have the limit as x approaches 0 of sine x over x? Well, if I replace x by 0, the sine of 0 is 0, replace x by 0. So I have this problem, and my three strategies so far have been factor, can't do it, rationalize, can't do it, there's nothing irrational, and simplify, can't do it. So, for now, I'm simply going to ask you to believe me, and if you look at it graphically. So remember, it was sine x over x. So let's actually graph y equals the fraction. Remember, we talked about the template. Sine x over x. Now, I'm going to hit enter, but I am going to go back and show you a better graph because we are doing a trig. So if you do menu 4 for window, and we're going to use option 8, which you'll notice over here is zoom trig. So you get this graph here. I could alter it a little bit more. Notice it doesn't seem to go any higher than 1, so I'm not going to have all this stuff on top and on the bottom. That's kind of useless. And I'm going to expand to see the size. So now I'm going to go into menu 4, which is window, and I'm going to set my own window settings. So I think we agreed that we don't need such a low. We can say mine maybe -2. Make sure it's -2. We don't need to go as high as that graph goes, so let's make it 3. And I would like to go further to the left so you can see more of what's happening. -20, let's say, to 20. Whoops. And I think I might have to change that negative to this negative right here. Okay. Not a good graph. Alrighty, we're going to adjust that one more time. And we're going to make that even smaller. I'm going to have that go from -1.2 to 1.2. I know exactly what the problem is. We are in the wrong mode. Okay, so doc 7.2, and I'll bet you this, well, it is in radians. All right. I'm going to go back, and I'm just going to leave it at that original zoom trig graph. Okay, so it looks, if you look at the picture, okay, considering every one of these tick marks is 0.5, that's 0.5, that's 1. So it looks like the limit as x approaches 0 from both sides is 1. And that is actually a correct assumption. But what happens is, obviously, there has to be an empty dot there, because 0 over 0 does not equal 1. But the limit from the left, limit from the right does appear to equal 1. And if we were to also graph, which you can try on your own, 1 minus cos x over x, again, if I let x go to 0, cosine of 0 is 1. 1 minus 1 is 0 over 0. In this particular case, though, you'll notice as you approach 0 from the left, and as you approach from the left and from the right, you're approaching a height of 0. By the way, I did x over sine x. I did sine x over x up here, but you could look at it as x over sine x, because you could just replace this fraction. Think of it as 3/5 is the same as 1 over 5/3. Remember, with limits, you can break up sums, differences, products, quotients, pull out factors, and you can also pull out exponents. So that becomes the limit of the numerator over the limit of the denominator. And we sort of agreed that this bottom one was 1, so you'll see it also equals 1. However, if I, instead of 1 minus cos x over x, which is what I had up here, notice here that's 1 minus cos x over x, if I flip that, I actually get does not exist, because this fraction is 1 over the reciprocal of itself, And the problem is that this limit is 1, this limit is 0, as we agreed visually, and therefore I would get does not exist. And that's the end of video 1.3c.